First of all, I would like to thank you, all the organizers. It's a great honor to be here, and thank you for the possibility to do this presentation. And actually, my name is Miklos KOZLOVSZKY, and I'm working in Hungary at the Óbuda University as a dean of the John von Neumann Faculty of Informatics, and also I'm heading the biotech research center at Óbuda University. Basically, what we have done here is a massively parallel ventilation of patients, and the whole story will cover this topic. As far as I know, I will have about 30 minutes to talk about that, and after that we will have some sort of question and answer session. Please let me know if you have any difficulties with the connection or hearing me, and then I will try to change it. And okay, if everybody agrees, I will start it. Okay. Okay. So basically, thank you. So actually, this MassVentil project is a concept for handling large number of acute respiratory failure patients, and basically, probably everybody knows that we have this COVID-19 problem, and this is one of the potential solutions what we can use to beat this pandemic. What are the main issues what we would like to solve here? We would like to scale up the ventilation capacity for a large number of patients. We are short, globally we are short in ventilators, medical ventilators. We also would like to protect the medical professionals, the doctors and the nurses during the pandemics. We would like to enable large-scale remote patient treatment and remote monitoring of the patients. And also we would like to provide situation awareness for doctors and nurses during their work. Basically, maybe you can see at the background, this is from Johns Hopkins University. This is a well-known map about how the pandemic is spreading, and basically what we have created is not for the Americans or the Europeans, but basically mostly for the third world countries and Africa and some parts of Asia, where people doesn't have so good resources concerning medical ventilators. The mission of this MassVentil project is to develop a working prototype for a modular mass ventilator system, which is able to work under critical circumstances and can be used to simultaneously ventilate a large number of coronavirus patients in critical conditions. So basically, there are a lot of ventilations concepts already. Maybe you know, I don't know whether you see the mouse here, the pointer, but we've got the single person ventilation. This is a well-known concept. One patient, one device. This has a restricted setup. We use dedicated resources for that, and then we are using this and individually set up the ventilation parameters of the patient. There are no cross-contamination possibilities. It's like having a car or a moped or a bicycle. Actually, we are able to ventilate these people. During this COVID-19 pandemic, we have another type of ventilation concept. This we call co-ventilation, which is heavily used or frequently used by medical professionals who are running out of medical devices, medical ventilators. Usually we are able to put 1, 2, 3, 4 patients on a single device, and we are reusing the existing unallocated ventilation capacity of the device. So it means that most of the patients should be the same type, the same severity level. So they need to be the same same age, same type, and such things. So this is basically a group ventilation setup, and similar people are ventilated with a single-use device. This is actually a hacking. It's against most of the suggestions and regulations of the different medical societies, because such devices are not meant to survive such large load ventilation, and usually they are just broken down after a while, and the cross-contamination is a valid possibility there. So it's like the same as the single-person ventilation, but as we are hacking the system, sorry, just a moment. Yes. It's like sharing a moped or a bicycle, which is usually against the law, but if we have a need, then we can do the transport. Concerning the mass ventilation, it's actually a brand new idea. So in that case, we are able to ventilate many people. Many means 10, 15, 20, or even more patients per system. This is not a device, this is a system. So that means that we've got a large-scale setup, use allocated resources, and we are the same way as with as it is in the single-person ventilation. We are using individual ventilation setup to ventilate the patient. So the patient is able to breathe, or as he wants, or the doctor is able to set up an individual ventilation method or mode. So because I will talk about later the internal architecture, no cross-contamination is possible. And if I would like to have an analogy, this is like a public transport. So instead of using a car, which is a personal transport device, or a bicycle, we are building a public transport like a train or a metro line, and we are sharing some parts of the device, of the system. That means that it's more cost effective, and then you are able to gain a lot of things. Later on, I would like to talk about that. Also, the similar analogy is the water pipelines in the city. This analogy comes because the internal structure and the way how it's working is similar as in water pipelines and the water resource installed usually in a city. What are the essential system features for all who needs to have all these things very quickly? We can identify 6 different things. First, this system can ventilate large number of patients. It's not a co-ventilation. The patient ventilation parameters can be set up, adjusted individually, like oxygen concentration, pressure, respiration rate, or the amount of air, which is the volume, which is put inside the patient. And also there is a free breathing support. So the patients who are in this system, they can breathe as they want. So there is no restrictions in breathing. We are transporting the exhaled and inhaled air. We've got the air management system, the transportation system, and because we are transporting the exhaled highly infectious air from the patients, we are also helping the medical staff. And because this is a one-way airflow, and we are also filtering the air, so we are reducing the risk of cross-contamination significantly. This system is able to go and work in a standalone way, so we are able to install it in a non-hospital environment. And also we are creating a software which is using a centralized dashboard. So we are able to see remotely all the patients on the single dashboard via network. That means that the doctors are able to have So they've got an overview about all the patients, and if there are some problems with the patient, then they are able to spot immediately where this patient is, and they are able to go there. If we are talking about many patients, like 50 or hundreds of patients, it's usually located in a ward or in a big room, and it's usually very hard to check all the time each patient's manually. So with such dashboard, we are trying to help the doctors. On the other side, we've got also a ventilation control, but the doctor is able to do remotely. So he's able to adjust remotely some parts of the ventilation parameters, which is very handy because the doctor doesn't need to go there close to the patients. He's able to do it remotely. And last but not least, there is a system support for non-invasive ventilation modes and also for invasive ventilation modes. The non-invasive ventilation modes is usually when you are using a face ventilation mask, and in the case of invasive ventilation, we are using usually an endotracheal tube. So this is the main concept. Are there any questions, or can I continue? Okay, so this is the concept of the mass ventilation system. Basically, there are two main parts. First part is the air duct system, which is transporting the air, intake air and exhalating air to and from the patient, and the patient is in the middle, and he is getting the air similar way as you are in your bathroom and you are in your bath and you are opening up the valve of the water pipeline, and the water is coming out because the valve is adjusting the amount of water which is going into your bath. The similar way we are using this similar way we are adjusting the amount of air which is transported to the patient. So at each patient there is a personal ventilation unit, and then this ventilation unit can control the air, the pressure, the oxygen level, percentage, and such things. Okay, if we would like to go more deeply inside the system architecture, you can see here that all the parts are supervised by a central IT, so information technology infrastructure. Basically, we've got the A zone and the O zone. Here is the air is coming inside, it's going down, and we are distributing this. This is a pipeline, and we are distributing this air at the patient zone, at the P zone, and then we are collecting from the patients the exhaled air, and we are then just pushing out with some negative pressure. So to say that how it's working, this has a positive pressure, this part has a positive pressure, about 80 millibars, and this part has a negative pressure, about minus 40 millibars. And basically, here are the motors. Because of the redundancy, we've got minimum 2 motors, which is in the inhale zone, and we are protecting these motors with filters here and here. And then at the other side, before we are exhaling the infectious air, we are also filtering it with HEPA or ULPA filters, which are cleaning out all these viruses from the air. I don't want to go more deeply inside the internal architecture unless there are some questions regarding this. Basically, we've got the bus system, we've got personal patient ventilation units, and we've got the IT infrastructure, which is collecting the data, visualizing the data, and also sharing the data, and saving the data, archiving the data. And I've got a video. So if you let me, then I will also. Can you see it?
Igen.
Excellent.
A MassVentil rendszer képes kórházakon kívül ad-hoc helyszíneken is üzemelni a megfelelő orvosi szakszemélyzet.
As you can see, actually, this is the testing site at the Óbuda University, and we have created already.
You are showing the wrong tab. We see the presentation tab and not the YouTube tab.
Sorry?
We are seeing your presentation tab, but not your YouTube tab.
Just a moment. Then I will switch. Just a moment. Thank you. Yes. Oh, yes. And then this. And then this. Yes. Are you seeing now?
Yes, we can now see it. It is muted, I believe.
Yes, because it's in Hungarian, but actually there is a subtitle. So so basically here you can see that this was the first prototype around in March. This is the valve system what we have constructed. This is at the patient side, and this is a simulated lung, so to say, what we are inflating, and then we are checking the pressures and all these things. This was the first prototype of the dedicated motors. So actually, as you can see, this was a strong prototype. So we are using two types of motors: one inhale motor and one exhale motor. And actually now in this setup, it was just near each other. Usually you need to have more space between these two because you never want to exhale and then inhale the same infectious air, even if it was filtered by ULPA filters, ultra fine filters. And then, sorry, yes. So yes, so we have these two pipelines, and these two pipelines are going the patients, and then these patients can inhale and exhale as they want. We are using these two type of buses to do it. As the air management is a common air management, we are using commodity of the shelf type motors. So the cost effectiveness is really good. The same way as you have similar in the public transportation, if you are comparing public transport to personal transportations. And yes, so then I will move back. Now we try to switch back to the, yes. Okay. And then for me, this is a new way of disseminating our things. So, okay, so this was the second type of setup what we have created. Here you can see at the right side that we have these two pipelines. One pipeline is for the inhale, the other pipeline is for the exhale air. And here are the different type of devices. These are the personal devices who are doing this patient ventilation. So basically, the internal architecture is quite simple. We've got a motor, and we've got these two tubes, and one tube is used to inhale the gas, the other is used to exhale the gas, and also we are using another one which is not at this screen for the oxygen. So what are the targets? So actually, we are targeting with this concept third world countries basically. So we are creating the how-tos and the blueprints We have created an open software, which is a community built type software. We are using off-the-shelf, easy to purchase and easy to produce materials for these people. We are trying to do the minimized development time, which is really difficult because we are building up a ventilator, a medical ventilator, which is, I think, one of the hardest medical device, because if you are doing in a wrong way, you are able to cause injuries, severe injuries, or even death. So we are creating the building manuals for this system, and actually we need to keep this in a low cost section, and we are creating this for populations who need this, and actually it's free to use. This is the milestones what we had. So we are started this in March. Middle of March, we had created the first single patient ventilator. Well, it was used with a vacuum cleaner. We have also, after almost at the end of March, we have improved it with some dedicated motors. Then we patented the whole concept. Then we used new type of valves, and now end of March we had the first version which was able to provide PEEP. People who knows what PEEP is, it's so basically you need to left some pressure in the lung if you are trying to ventilate ARDS type of patients, acute respiratory disease patients, because otherwise you are not able to ventilate these people. So simply say, this is what PEEP is, so the residual pressure what you need to leave in the lung. Then we have created in the beginning of April the 3 patients setup. Then middle of April we were able to make 5 patients simultaneously. We are able to ventilate with a single setup, and we have now a new. In the beginning of May, we had a new valve which was already containing the safety and also the oxygen input. Last week, just some things recently about the status of the things. Last week, we won the EU versus virus hackathon, which was about 21,000 people from Europe, from 27 different countries, and also from other countries in Europe. And it was more than 2,000 solutions, and we won the first place in the Life and Health Challenge, which was targeting medical ventilators. And also we have now a new valve. Actually, what we received from the manufacturer, we have released the new dashboard UI, and we have also finished the box design of the valve and the patient ventilation units. And these are the future targets. So we have actually the aim to make a strong prototype. It's a pre-product, and we are using for this pre-product, so to say, medical grade professional components instead of budget components. Maybe you already saw in this place. So these are actually normal water pipelines and tubes and pipelines from the hardware store, which are not essentially medical grade devices. But we are also creating another type of strong prototype using professional components. And also we are creating the documentation which is suitable for medical device manufacturers. And but to build such system and to enter the market with such system, it needs a more robust design and more so that it needs a longer development time. So the time to market is about 1 year instead of some months. We have to go through all the clinical trials and the testing and validation, and the certification based on certain type of standards, and actually even this is free to use during the pandemic. Our plans is to finish now the first transportable version of the system. So we have now a container, and we are including all these devices inside a single container, so we are able to transport this, and then it's much easier to deploy it in an ad hoc hospital. So we have already an agreement with the Hungarian government, and there is an ad hoc field hospital installed and deployed in a convention center in Budapest. So we are now deploying our system there to make more testing within 2 weeks. And this setup will ventilate 10 patients parallel. We are already doing this, and we are using new motors, more reliable devices, and also we are now releasing new software and prepare all the documentations. There is also a short-term plan for the EU Matchathon, which will be in May 22 till 25, which is organized by EU Research and Innovation, and they are actually providing matchmaking between the teams and founders and companies. So I need to say that this is not a a one-man show, so to say. So we've got more than 40 active co-workers from over the university. Most of the faculties are working on that project. The Faculty of Informatics, the electronics, mechatronics guys, and people from the light industry faculty. We have a lot of hardware, software, legal, PR, and marketing people on the board, and I would like to thank all these people actually here and on all the events that they are doing really excellent job. Besides that, we've got a community with more than 1,000 visitors, and also about 1,200 professionals who are supporting this community build with all the different expertise and knowledge. So, and also I need to mention the universities where the students are very much interested, also in Hungary and also in other universities around the globe. So basically, I had this presentation, and thank you for your attention, and I'm really looking for questions if you have, so please let me know.
When you ask your question, please remember to unmute.
Yes.
First of all, I just want to make a comment. This is truly fantastic. When I first learned about the project, I was very, very impressed. And I'm more and more impressed as I see the progress moving forward. So congratulations.
Thanks, really thanks.
Ludwig, we cannot hear you.
So, sorry. My name is Lajos Galambos. Can you hear me now?
Yes.
Loud and clear.
Okay, so the question that I have, what's happening with the air that is coming out from the lungs of the patients? How do you deal with that? Do you have a scrubber?
It's a very, very good question. Actually, we have this exhale bus, which is sucking out the air with this minus 40 millibars, and we are just transporting it. And at the end, before the motor, we are filtering it. And after the motor, we are also filtering it. And we are now using also UV light to have a third sterilization of the air, and then we are exhaling it to the free space.
Mm-hmm. Mm-hmm. Yeah, thank you. And can you say anything about the cost? How much would be?
Okay, cost. It depends. As maybe you grasped it. Two types of way we are using. The first is a budget solution, so to say. In this budget solution, we are using commodity of the shelf type of things like pipelines for the hardware store and other devices. What you are freely able to buy. And in that case, if you are building up such system, I can give some rough estimation about the components. So the motor, what we are using is about $15.
Mm-hmm.
One motor is able to provide enough air for about 30 people, 30.
Impressive.
And the pipeline is usually not a very much costly thing. So if you are so this is the pipeline and the duct system and all these things. Of course, if you want to increase the redundancy and the robustness, you need to put more motors, and you need to adjust high-grade materials and all these things. On the other hand, at the ventilation side, each patient ventilation unit you need to create, and you need to put at the bed of the patients, because this is actually closing and opening the valve system and giving enough air with or without additional oxygen. So this part you need to buy for each of the patients what you want to ventilate, which you want to ventilate. That means that this is about you need to create a board, a controller board. We are using a microcontroller. This ESP32 microcontroller is about $7. We've got 4 pressure sensors, which cost about $20, and then the board, and then we've got an MR17 motor, which is cost about $10 or $15 maximum. So in total, I think you are ending up about $200 or $300 per patient.
Wow, that's much cheaper than that's on the market right now.
So if you are building up, a massively, sorry, I've got a big echo here. Could you please mute the microphone?
Yeah.
Okay, thank you. So if you are building it from so to say from scratch and building up from non-medical materials, you have about 1 to the 100 the price difference between a normal medical ventilator and such device, and you are able to ventilate 10, 20 people.
Wow, impressive. Because right now a ventilator, it's around $14,000 individual
exactly.
one.
In $40,000, you can build up a system which can ventilate about 40 people or 30 people, let's say. Okay, so but this is not medical grade, and that's why we are targeting actually the third world countries, because usually these people doesn't has enough money to buy medical ventilators because it's a costly thing. But if they are skilled and they have engineers, they are able to build up such system, which is much better than nothing. So this is an emergency solution, but they are able to create, and we are giving the software and the blueprints and the building materials, and they are able to put it together. So they don't need to try and make the trial and error, and they are able to buy it from hardware stores, so to say, most of these things. If we are talking about a medical grade system, then I don't think so that this will be much cheaper than a normal medical ventilator. However, we are able to do a cost-effective building because we are not including inside the system, let's say for 50 persons, 50 motors. We have 1 motor or 2 motors or 6 motors, but the cost of such motors is much lower, and the valve system at the person is really cheap. Because the valve system is a dummy tool which is just opening and closing, and the air has a basic pressure in the system. and that's why it's much more effective.
Okay. Hello.
Hi.
Hi. Okay, I'm Nasser from Nigeria.
Nice to meet you.
Thank you very much. It's quite interesting what you have. So, what will it take for someone to get the software and the blueprints from?
So some blueprints are already on the web, and we are creating it, and we are how can I say it? So we are behind all the documentations. We are much more forward with the development, but we are catching up. So we will release the new versions of the documentation end of this week. And actually all this type of documentation is free to download from the website at the MassVentil.org.
Okay.
We also looking for teams who want to join and who want to build together with us some examples, some conceptual prototypes outside from our university, because actually we are upgrading all the time with new software and hardware, and we are sharing this knowledge with the others who are building up such devices.
Okay. Thank you. I think we're interested. We're very much interested because we're coming up with a team. We have a team actually, so we're trying to see how we can produce this, and it will help a lot with, because considering I think you mentioned a ventilator cost about $14,000. Over here now, the prices has gone up to about $40,000, 40, which is crazy. So having something like this would actually help. And if you look at the numbers for infection over here, it keeps rising. Today we've reached the 3,000 mark, which is just, we don't know what is going to happen in the future. So I think this is a very good idea, and this is something we would love to work with together.
With pleasure. Thank you. Any other questions?
I saw a question from Eva Geru. Maybe you can unmute yourself and ask a question.
Just a moment, I will check the text and then I will. Okay, the question was to disinfect the exhaled air. Simply through bubbling over a disinfectant, liquid detergent in water could be considered past the motor and filters. Yes, but in that case, you need to put at all the beds such can which contains this type of liquid detergent water, and you need to change it and you need to monitor it, what is the status of this type of water inside. So basically we consider this, and actually after when we have released our first prototype in Germany, there is another team who was building a similar system based on our idea, and they are already created such device with this water, this liquid detergent cans, which are at the bed of the patient. You can do it, and in that case, you need to have some sort of quality assurance that you are killing all these viruses, and you need to monitor all these waters, the quality of this sterilization, which is not an easy thing. So that's why we said that we are just sucking out the air, and we are filtering this with filters at one point. And until that, the whole system is a single way duct system. So we are not letting out the infectious virus and gas to infect the medical professionals or other people around the patient. But this is really a good way to handle it. it's easier. I need to say that if you don't have filter at the end at the motor, then this is also an option to make it in a centralized way. The only thing is that we are using this type of filters because we have these filters, and these filters has a very effective filtering capability. Of course, it should be changed in a regular manner. Yes, in that case, it's valid and feasible. The question was, I mean, to place it at the end point in a centralized place. Yes, it's feasible. Any other questions? Please.
I have one.
Yes.
Have you considered a simple scrubber to, instead of filters, let's see, people who cannot change filters or don't have, or you try to avoid this liquid filtering system, you can use a scrubber. So a scrubber is a high temperature chamber. The air goes through it, and the viruses will die. So it's very commonly used in the industry all over. Well, what you need is to plug it in, and it has to go through it's just like a muffler.
So you are killing all these viruses with heat.
Exactly.
That's a valid option, but we are able to do only in the exhale part, because we are not able to disinfect the air when we are doing in the inhale section. For this, you need to have some sort of filters. Otherwise, you need to heat up the air, and then you need to cool down, because people need to breathe it in. Actually, I didn't said much about the temperature and the moisture of the system. So how we are able to handle the moisture and the temperature. Usually, when you are ventilating patients, you need to target a certain amount of temperature, air temperature. Otherwise, you are just making these people more sick. So we are using HMEs. This is a humidity and temperature exchangers, which is placed at the patient near the mouth, and then the patient, actually, when he's exhaling, then automatically this has like a sponge inside, and then and the patients exhale, watering this sponge, so to say, and then the inhale is the temperature and the humidity of the inhaled air is adjusted automatically. So we are not using in the main duct system any temperature control and any humidity control. Only at the beginning, if there is a hot air, because in a desert or in some places it can be a very hot air, so we are able to cool down this air before we are entering inside the system such air. So, but for this you need electricity and you need the air conditioning system.
So Miklos, UVC light won't work?
UVC light for disinfection?
Yes.
Yes. Maybe I mentioned that at the end, when we are exhaling it, after the HEPA filters, we are now using HEPA filters, but you can also use ULPA filters. We have one part which is using a UV light. The only problem with the UV light, in case of a budget system, most of these PVC tubes are not protected against UV. So if this is a powerful UV light, which is killing all the viruses, usually you are also eating all the plastics around the UV LED. So that's why you need to use metal tunnel or metal duct system at that section. But it's really a valid solution. We are not using as a primary virus, that disinfectant, virus killer, because it's very hard to be sure that you are not letting out viruses only when you are treating the air, which is flowing quite fast with UV light. And you need to be sure, because otherwise you are just blowing out the air, which contains a lot of virus, and if somebody is just there, it can be a harmful thing.
Again, Lajos, so there are complicated and simple ways to solve these problems. So if you want to be very sure, you have to heat the air, because any organic materials will die at 400 degrees C. So you have to go to certain temperatures in order to, then you need a spectrum analyzer to see what's coming out, and to see if you have any. So before it goes through an FDA or any other country that will allow it to be purchased or built, the masses. So there are some safety procedures that need to be.
Yes. Okay. Yes.
So I know the concern is the exit and yeah.
Yes.
Yeah. Thanks. It's very interesting. It can triggers a avalanche of questions and thoughts. Very good. Thank you.
Actually, it was we contacted a lot of people before that. Before we said that this can be a feasible idea, and nobody was ever even tried to make mass ventilation, because this is a personalized thing. So people are breathing as they want. So, but the same thing, that if you are in the bath tube, you are opening and closing the valves as you want. So all the people in the house can open and close the valve and get the water as they want. The only thing what you need to be sure to give the pressure, the basic pressure, because if you are opening too many valves, then the pressure is dropping down and you don't get enough water or air. Actually, I can go here and I can show you also something. Maybe it can be interesting. Just a moment. Can you see it?
Yes.
Okay, so in the presentation there is one part which I was not talking so much about. This is this. So basically this is a modular system, and you can see that these are the segments. This is one segment, and on the other side this is the same segment, but this is the exhale zone. But we are able to create dynamically additional segments. So you are able to increase the amount of patients when you want to ventilate more and more patients. And these are not disturbing any ventilations of these type of patients who are already on the system. So you are able to dynamically extend the system with additional segments, which may be usually good to have such things when you are dealing with massive pandemics. I have also another question. Okay, no, it was just, yeah. Okay. Any other questions? Actually, that was really an excellent question. So I'm really.
I think you muted yourself.
Okay, so it was really excellent question, and all the questions actually were very good. So I was really enjoying it. So
good. Well, if there's no other questions, then we'll let Zoli to wrap up. And yeah, thank you very much for the amazing presentation. And we make sure that we share the presentation with all the attendees.
Yeah, and one more thing, Csaba, maybe Miklos, you want to share that there is a GoFundMe page for this project.
Yes, I totally forgot it.
You can contribute to the project if you would like, or share it with others.
Yes, basically there is a GoFundMe project site, MassVentil, and actually we also relying very much on the community, and so they are very, very generous, and I'm also very thankful that they made it, because actually we were able to build up until now 3 full-featured system, and we are also trying to make now this transportable version, which we will have. And in this transportable version, we are using a container, a 20 feet container, and we are also installing inside and deploying inside all the IT infrastructure, cooling system, and all the redundant motors. So at the end, we will have a transportable system which can be later on deployable within some hours, which can be useful, I guess. And actually, this is just a feasibility study whether we are able to create this type of container, because later on this can be very useful, because otherwise we've got this medical single person medical ventilators, and usually they consume a lot of space, and it's very hard to manage and monitor all these devices. Usually these devices are beeping, so if you have 50 people in a ward, or in a football field, and all devices are beeping the same way, the same frequency, and it's usually very difficult to handle such amount of single island-like infrastructure. So we're also trying to create a software which is homogenizing all these different patients, and we are providing a single one-stop dashboard where the medical staff can see what is happening with the patients almost in real time, within some hundreds of milliseconds, and that means that you are able to use the human resources much more effective. In case of pandemic, the doctors are raw resources usually. And thank you, Josef.
So if we don't have more questions, thank you very much again for the wonderful presentation, and thanks for all the attendees to attend here. And I would like to remind everybody to take a look at Hungarian-SV.com to see what other presentations we will have upcoming, and to sign up for notifications for that one. Thank you very, very much, and that was a fantastic job.
Thank you very much. See you. See you. Bye.
See you.